The title of his presentation is What It Takes to Advise a Successful Competition Team. In case you're wondering, so a little background about Dr. Radovich and his accomplishments. He received his PhD in aerospace engineering from University of Southern California in 2010. Prior to coming back to University of California in his current position, he worked in industry and launch vehicle, spacecraft design, aerodynamics, and wind tunnel testing. You see some of the companies listed there. He is the director of aerospace and mechanical engineering instructional laboratories at USC. He's been a faculty advisor to 5 student competition teams, programs, and labs. And some of the accolades include the 2010 and present, the AIAA Design Build Fly competition. They won first place, not just one time, but 3 years. And I tell you, I had the opportunity to advise a group of students for AIAA DBF a couple of years. It's a lot of work. So I certainly know how much effort goes into doing that, and the fact that he was able to get the results that he got from his team, that's remarkable. And they also won the second place in 2011. So with that, let me stop sharing my screen and turn the floor to Charles. Charles, the floor is yours.
Thanks for that warm introduction. And just can't say what an honor it is to be able to just be with all of you tonight. I know we just spent, as educators, a heck of a year. We're all battle tested. We all have the same types of scars. So just to be able to spend an hour or so here with you all is just it's really something. So I just want to say thank you for having me. Thanks to Phil and the committee for extending the invitation, and I'm pretty excited to be here. So with that, I assume I can share my screen.
Yes, you should be able to.
I dumped my slides into the chat there just in case anybody wants a copy of them or wants to follow along separately. And then I'll just kick off slideshow mode here. So yes, good evening, good late afternoon, everybody. I'm here to talk about what it takes to advise a successful competition team. And I'll start off with a kind of a brief intro, since most of this was covered already. And yes, my name is Charles Radovich. I did all my studies here at the University of Southern California, which is where I now teach. My areas of research and expertise have been experimental fluid mechanics. And if there's a wind tunnel test I can get involved with, I certainly will. And so I'm in the Department of Aerospace and Mechanical Engineering, director of AME Instructional Labs. That essentially means all undergraduate laboratory work in our department. We have a lab, and I direct that, and make sure our students, I get as much lab experience as they can. I oftentimes try to get standard lecture courses to introduce a hands-on project or just anything we can to get more hands-on work going. My title as a teaching faculty member is Associate Professor of Engineering Practice. Some of the things I focus on are experimental lab courses, typically the junior and senior level courses, capstone design project included with that. And general topics include, for other lecture courses, basic flight mechanics, fluids, intro to aero. Other things I do, faculty advisor currently for 2 different teams, the USC AeroDesign Team, as well as a spacecraft propulsion energy laboratory. The AeroDesign Team is one I'll focus most of my talk today on. A little bit more about my background and research, just the things I've kind of experienced from the academic side. This commercial truck testing over here, that's road testing, which started with wind tunnel testing. So looking at fuel savings for, attachments on the base of a vehicle. Trucks in tandem, kind of exciting to see. Base flaps have been around for a while. Trucks in tandem keeps getting more and more attention. Fleets, to actually see that stuff, 10 or 15 years later, actually make it to the road. Experimental fluids highlighted there, and then other experience, AeroDesign Team. So I'm not only an advisor now, but I was an active participant as a student in my undergraduate days. Outside of academia, I also have a bit of industry experience. So quite a few years at SpaceX, starting on the left over here, Falcon 9 version 1.0, and then 1.1, which was reusable, and Crew Dragon launch abort also highlighted here. So all areas that I've worked on. We're involved with aerodynamics work, a lot of unsteady aerodynamics and buffeting in particular. After leaving SpaceX, I did a little more consulting work for Virgin Orbit and their Launcher One vehicle, which finally has flown twice now in this last little over a year. So exciting to see that. And most recently, I've been able to contribute to some of the foundation and groundwork involving aerodynamics for relativity space, which is kind of a cool endeavor because the founders are 2 of my former students. So it's kind of neat, as I put it, interning for them. So continuing with a little bit of introduction on my department in USC, just to give you an idea, where we come from. So to help you understand or put into context the way we do things, which I think allows us to be successful in the design team world. So the Department of Aerospace and Mechanical Engineering, give you an idea of our size. We have 35 full-time faculty. That's mostly full-time, well, mostly professors, and implying that they're doing research, carrying on research groups. There's a breakdown of full associate assistant professors given there, and 9 teaching faculty like myself. So various levels of engineering practice and full-time lecturers, kind of filling out our faculty profile. As for our students and our class size, we typically admit about 115 freshmen each year, plus about 20 transfers trickle in, maybe their sophomore or junior year. As an engineering school, we've achieved a 50-50 gender parity. I'll tell you, AME is a little lagging on that ratio in terms of, say, just catching up, but we're getting closer. It's something we're all pretty proud to have achieved recently. And then the rest of the department.
As you should be, sorry, that's amazing. Good for you.
Yeah, it's pretty, it really is pretty cool to see. So the rest of our department, 375 master's students. There's a lot of remote students there. No doubt that's our moneymaker. And we have our distance education network, and then about 100 PhD students in our department. In terms of our undergrads, we're kind of taking a turn to focus a little bit more on our undergraduates, and we'll steer this towards design team work. Just what they're involved with, what our students do. A lot of them partake in research, 10-hour-a-week work study type jobs. A lot of them are involved with professional organizations. I'm sure, like many of your students, the kind of the bigger ones here I've highlighted. And then a big part of our culture is design teams. And so design teams, I highlighted this in red because I think it's a kind of a big point worth making, because it might be different from your university, is our design teams are run as extracurricular student-run organizations. So they're open to all USC students, not tied directly to any course or any major. And I think this is the difference maker in terms of how a lot of our teams are able to be successful and enduring. Everybody that wants to be on these groups is, everybody that participates wants to be there. And I've seen, and I'm sure anyone that's advised a team, go to a competition before, and you can see the ones that were there because they had to for class versus the ones that have been burning the midnight oil, hanging out in labs, having fun with their colleagues, if you will. And so I think foremost, that is perhaps the most important factor I see in terms of the way we're able to run our student organizations. We have a lot of them. And just to name a few, the AeroDesign team, we also have the Rocket Propulsion Lab. We have 2 race car teams. There's the Formula SAE Combustion and the Formula E Electric team, which is new for us. There's a recumbent vehicle design team, which is also known as human powered vehicle. The Advanced Spacecraft Propulsion Energy Lab, that's Aspen, the other group I advise. A solar car team, concrete canoe, and steel bridge. I put a couple stars there because those teams in particular don't have very high concentrations of AME students, but there's always some, which is another highlight of being extracurricular. Anybody from any major can join and participate with these teams. All of these groups are set up to compete in some sort of international event. Typically, I will say, Rocket Propulsion Lab kind of just does their own thing in terms of, they currently own like the student-built altitude record for a home-built rocket that was fully recoverable, so they're just kind of setting their own targets, but everyone else for the most part is tied to some sort of internationally recognized competition. And the funding sources, I'll get into more details here in case someone's curious what we spend. I'll spill those beans later, but in general, to keep these groups running, our funding sources come from 3 different pots. The first one is our engineering school, and that's typically for raw materials. And the idea is submit a proposal, get recognized, and funds will be granted. The university provides funding as well, and that's typically for travel and putting on professional or networking events. And then we also rely quite a bit on industry sponsors, in particular Boeing, Northrop, and Lockheed Martin donate substantially each year with not just as say a lump sum to the school or the university, but with dollars spelled out directly to go to certain design teams. So they're targeting our design teams specifically. To give you an idea, just some of the things that our students build. This is the Rocket Lab, so we're talking about real hardware. That thing went to space. There's our human-powered vehicle, one of our race car teams, the concrete canoe and steel bridge. And in terms of how all these teams are structured, we do try to have them mimic like a startup culture. So very collaborative, scrappy. They self-teach themselves. They transition knowledge from senior leadership to younger members of the team. And ultimately, they all have a very strong sense of ownership in the work that they do, a lot of pride that comes with it. All right, so now I'm going to spend the rest of the time here focusing on the details of the team that I advise, or one of the teams I advise here, the AeroDesign team. This is the one that we've had quite a bit of success with. A little bit of overview on the team. And we compete in the annually held Design, Build, and Fly event, hosted by the AIAA, as well as Textron and Raytheon. This is an international event, about 100 teams each year. We build a remotely piloted aircraft. And one of the things we like about this competition is the design requirements change each year. It's not like we know exactly what we're going to build each year in terms of size or scale or mission requirements, so it really keeps us on our toes. And another cool part about the rules is they oftentimes reflect the real world challenges. Like I can imagine whoever wrote the proposals probably has this work to do at their job, in the real world, and they're trying to get the next round of talent to hire within the next year. And as an example, distributed manufacturing was a theme one year, and that had, we had to build an airplane that could carry around another airplane or parts of another airplane. Our objectives for any competition is complete several flight and ground missions. So the combination of speed, payload, endurance, ground operations, and sometimes packaging, like if it can fit in a tube, if it can come out of a box and be assembled in a certain amount of time. And another major component of our yearly effort is a 60-page technical report. My team has about 30 active members, give or take, each year. Any major, but they're mostly aerospace engineers. But we do cross-pollinate whenever possible, however possible. And one way we do that is the start of each year. We, of course, have like the student activities fair where people can come by and check us out, but we actually go to the freshman level and the undecided and sometimes even junior level, up to the junior level classes for other engineering majors, and in particular, computer science. Since we have a lot of students that don't have that skill set, we try to go and attract engineers with other skill sets by presenting 15 minutes, 10 minutes or so at the start of somebody's lecture, bring some hardware, and that typically gets people excited. In terms of how we operate for a given year. Here's our typical project schedule. It is year round. So late August, early September, the rules are released, and we immediately kick off into our preliminary design phase. This comes to a head with a design review with industry professionals. I'll get into more of the details on that later. As soon as that phase is done, then we hop into our critical design phase, which again ends with a design review with a bunch of invited guests. Then it's iterate and work on that competition build all the way up until April, where we compete. Shortly after that, a couple weeks to recover, get ready for finals, and then the team has elections, but the year doesn't stop there. May through August is also very active. We have new leads in their new roles, and they'll all go through the motions. They'll typically take the previous year's competition or another year's competition and modify the rules a little bit so that they would have to create something new, and everyone can now operate in their new role. And they do this as a way of minimizing the startup transient in September. So when those rules come out, like a well-oiled machine, we're producing planes and getting ready for competition already. The history of the team is we've been doing this for over 30 years now, and it started in 1991. It was founded by a student, Wyatt Sadler, and Professor Ron Blackwelder. So he was the faculty advisor at the time. And so Wyatt is now an advisor on the team and still the team's pilot consecutively ever since he founded the team. He's never disconnected, which is quite amazing. And Ron, although he's retired, still attends our design reviews and meets us at every single competition. So this says a lot about the team and the way it was built from the beginning, thinking about the future, the foundation, contributing beyond the years that you're active as a team member. And these two set the tone for that and continue to demonstrate that through example. 1991 through 97, the team started by competing in the SAE heavy lift competition. And then 1997, the AIAA DBF competition showed up, a little more attractive in terms of the design variations and challenges. So we started doing that and have been there ever since. So as noted before, we have a pretty good track record, and of recent, we've been kind of on a roll, winning every 3 years. I'm going to put an asterisk next to the COVID year. A little tough to build when we could not be on campus, but they still did build a plane out of their homes, which I couldn't be more proud of. But our design report, 3 straight years of having the top design report, which again, something I'm kind of proud of there. Give you an idea of what we build. There's a couple pictures already, but I'll give you a range of kind of aircraft sizes. So something from 2 meters in span, 7 kilograms. This is about as big of a plane as we might build. Sometimes they get heavier due to payload requirements. But to put this into perspective, this is the type of plane that doesn't fit in someone's car. You need someone on the team with the truck. I turn out to be the only person on the team with the truck. And, competition, travel logistics, flight test logistics get a little more interesting. And we also have small handheld airplanes some years. Those are much more convenient for transporting and have their own set of design problems. So kind of like a 10x scale factor difference there. A lot of different solutions have to get evaluated or at least thought about. So to highlight the iterative process in one, depending on how you look at it, typical or atypical year, I thought you'd like to see this. That plane that I started with, the 2 meter span, was our initial concept. Came up with that after the rules were released, and we iterated towards a PDR design. Things got as small as they could, weigh as less as least amount as possible. And what's typical is the rules might change halfway through the design year. And now things, maybe the scoring analysis or some constraints applied. So we refine our design and things get smaller. And we're like, okay, no longer foam wings, but we have to be competitive by using wood. So we have balsa wood or stringers. And then rule change number 2 shows up. Scoring analysis changes dramatically. And all of a sudden we're looking at hand-tossed airplanes. And so I highlighted in there PDR, that first rule change in this year came out the day we were giving that presentation. And CDR, several months later, you can see how far we had drifted from our initial thoughts. What do we do for the rest of the year? CDR say in February, iterate, iterate, and iterate until we get to as optimized of a design as we can for competition. Yeah, that was 1 year, but it coincidentally highlights the full spectrum of aircraft sizes that we build. All right, so how do we iterate? How do we design? What are our aircraft sizing methods? We start by score analysis. So they give us scoring equations, do partial derivatives, things like that to just understand the sensitivities, figure out the variables that matter. So these are the driving variables in the design, the things that we need to focus on first. We also take a look to see if anyone might game the competition. We call it cheese the competition. You know, the rules might say, divide, you know, not divide by, but the rules might look like carrying more payload is the best way to do it, but sometimes carrying no payload or, you know, 1 golf ball instead of 50 allows you to get into some corner of the design space that might allow you to win. So kind of look for anyone that might be able to game it, and maybe we're looking to game also. Where do we go from there? Just first principles for initial sizing. So hand calcs, historical trends, payload fractions, what's possible, what's typically possible, what are typical thrust to weight ratios. We have a lot of data. We have 30 years worth of data, so let's use it. There's also the competition field, their data's out there. So utilizing that stuff just to gain a sense for what's gonna be possible in a certain size class. From there, we do what's called what we call brute force energy analysis, and that's what this fancy plot on the right is. It's a very large variable space, but kind of low fidelity inputs. The plot in particular this is a 5-dimensional plot. There's 3 axes labeled. The color gradient represents the score, and the size of those dots represents some quantity of payload that was being utilized or being modeled. And I say it's a low fidelity type of analysis because we're not doing too much modeling of, say, the physical components. Essentially, this is, if I have this much mass, how much energy will it take to, propel this thing around in competition laps? But it helps us identify where we should focus the remaining part of our design effort. So once we're done with this, we utilize something called Plane Tools, which is something we named, but it's the team-built flight software simulation package or flight simulation package. It does the actual flight segments, like takeoff, cruise, models the turns. So definitely higher fidelity there. Also because it's using as tested and as built data for the components. So lab and flight test data, empirical models. It's actually simulating or modeling the real components that we're going to have in our aircraft. Everything down to, how do the batteries sag over time under a given current draw? So we're getting as real as possible as we can with that analytical approach. And ultimately, this allows us to refine our design for propulsion and aerodynamic optimization. This is the type of analysis that will allow us to say, do we need 6 cells on a battery pack or 5 cells? And sometimes it's the weight of those cells that can make the difference in terms of who's gonna place in the top 5 or not. Manufacturing methods, what do we deal with? Everything, whatever weighs the least, ultimately. Carbon, Kevlar, fiberglass, aluminum, plastics, even paper. If you can show something can get the job done and weighs less, then it's going to be a winner. What are the requirements? It's probably more important than just the manufacturing methods, but a very strong config lead, somebody that just loves doing CAD. A CAD repository is also very helpful. So if you have a very strong configurator, it's important that all of their files aren't on just their laptop. Not a lot of people can contribute that way, in parallel, and no one can learn from that in a following year. To manufacture and prototype, teams need space. And I highlight their layup table. We actually have one of those nice metallic layup tables where we can do really good high quality composite work. but a team's going to need lab space for that. So they're going to have to be supported in that regard. And of course, some funding is going to be required here. In particular, if you want to experiment with materials, if your budget's tight or you don't have, the time to explore a lot of options, then not as much money is, say, required if you know these are the constraints on what you could buy and purchase and build with. In terms of how our team is organized, there's really, let's call it 3 tiers. Starting with, in black up there, the advisors. It's faculty advisor, myself. We have our pilot and team founder, Wyatt, and he also serves as our industry advisor. And then we also have Ben Ackerman here, who's an alumni, graduated in, I think, 2012, and has not missed a Monday meeting ever since, and continues to advise the team and come out to competitions, test flights when he's in town. He doesn't even live in Los Angeles. After that, we have 2 team leads. That's a chief engineer and a program engineer. And then we have an assortment of engineering leads. So we try to model this similar to roles you might see in industry. Every year we reevaluate if the roles made sense, if the workload was getting distributed, say, evenly. Sometimes depending on the rules, like we don't have landing gear on a particular year, if it's a hand-launched airplane, then we might combine or eliminate some of these captain's positions. And it's something we pay a lot of attention to make sure we don't swell to have, way too many captain's positions, because that can just kind of water things down in terms of, say, ownership and participation. And one thing in particular that our captains are really, really, really good at is they train the less experienced team members insofar as, ideally in the first 5 months of the year, these leads won't touch any hardware. Maybe they'll help where needed, but ideally they're training less experienced junior members in doing what the team needs, creating propulsion sets. That's where the knowledge transition is happening, or where it happens. And when the going gets tough, they'll step in, and when we rally towards competition, for sure their hands are in the weeds. But they're fantastic at taking a step back and making sure the team for next year is set up before they get very headstrong and just hyper-focused on this year. Overall, in terms of how we run week to week, the team leads run the show. So things don't go through me by any means, but they're the ones that are in charge. They hold weekly general meetings. That's our general, student body meeting. The engineers get up there and, the leads present their recent progress, discuss challenges and upcoming tasks. The team leads also hold a weekly engineering lead meeting where they, focus in on design decisions, resource allocation, who's doing what, and setting the schedule for the week and for the year. And the team leads also hold periodic one-on-one meetings with the engineering leads. So essentially just like management would. I saw a chat pop up. I wasn't sure if that was intended for me or not, but I don't see it on my screen. I think because I'm in presentation mode, so.
It wasn't for you.
Okay, excellent.
Yep.
On to, say, myself as a faculty advisor, say primary roles, safety, make sure my students are just in a position to do what they need to and do so safely, so we don't get any red tape or any stoppage down the line. That starts with, we have some experienced, staff lab technicians give lab safety training each and every year, make sure our machines are in top shape, get rid of the stuff that seems dangerous, and just make sure we run a really tight ship. Ask questions and get conversations started, I view as one of my primary jobs. So during our meetings, just remind the teams of lessons learned and provide some continuity from the stuff we've done over the last 30 years. Tell them where to look, where resources can be found. Very carefully, I only advise them on things to look at, and certainly I've never told them what to do. I've never told them if it should have 1 wing or 3, if it should be an H tail or a V tail. But full ownership is in their hands on the decisions that they make. I'll certainly tell them to look at certain things or to validate their decisions with some sort of data. I do have to do a bit of, say, guiding the students on how the process of design can work. A term I like to use a lot is the biggest fish to fry. There's a lot of things to look at, but how do we quantify what matters? helping them, learn analytical approaches, and, maybe it's software or something like that, or writing scripts, or validation, most of the time through test efforts. How do we get the data that we need? Walking them through test campaigns, helping them plan that, and kind of keeping the standards up for our technical report writing, helping them, present data, speak about data, and just ultimately put together a technical report. And I do hold one meeting weekly with the team leads, but that's primarily for management coaching to make sure they're equipped to be effective leaders for the team. If there are any interpersonal issues that I might need to help with, or give them some tools or ways of working through certain situations, and just ultimately helping them to be the best managers that they can be. The industry and the alumni advisors are a quite special feature here to the team. They have a similar role as me during weekly meetings. We're just kind of in the audience and there to throw stones. Some of the industry or alumni advisors attend online, and we've always done that with Google Hangouts in the past, but it seemed like people like Zoom, and we had a whole lot more online participation from alumni this last year, so it's something we'll keep going in the future. They're really there to help maintain continuity from previous years. They're the ones that did all the work in the previous 20 years, so they remember things and can point our students in certain areas. And oftentimes after the general meeting, they'll pick up with them later in the week to have a little more focused discussion with engineering leads. In particular, manufacturing is typically something that will get discussed, making sure they're aware of the possibilities, and even goes as far as offering in-lab training sessions. Hey, this Saturday, alumni such and such is going to come to the lab to show us how to make molds again for composite parts. And they also help with analytical development. Maybe there's emergent techniques or software that students might want to kind of get some exposure to. And our alumni have been particularly helpful with helping us maintain our code repository. Again, just keeping in mind we're aerospace and mechanical engineers. We don't naturally think about GitHub and all that kind of stuff. So having the, say, more experienced alumni help us stay in check with best practices, and utilizing a code repo the way it should be has been very helpful. So knowledge retention is a huge part of why I think we're able to be successful each year. And so the idea here is, like, how do we keep 30 years of tribal knowledge, not only in-house, but accessible? And so as an example, it's just so easy to lose any information within a couple of years. If you had 3 straight years of balsa planes, that means basically no one on the team knows how to build composite structures. So what do we do to address that? We typically force a refresh of, say, out of routine skills into our August and September build sessions. So before the rules come out or while they're trickling out, as we're doing our in-lab training sessions, if we did a balsa plane the year before, for sure we're going to build a fiberglass wing, to start the year, or maybe we'll do both. And the summer design project, I told you they'll take the previous year's competition and change the rules, or they might force in a requirement that it has to be of a different construction type, and just force everyone to think in that mindset. This has also happened before, that we had 2 competitive designs. One was just a standard monoplane, and the other was a tailless aircraft, or some would call it a flying wing. And so either one seemed like it was going to be just as competitive from a scoring standpoint. So a team deliberately chose to go with the tailless aircraft because they had never built one before. And so that's just an example of the team thinking about how to push the boundaries of what they're capable of, and expand the knowledge base for next year's team. The team also maintains their own server. So they have a website which has some outward and some inward facing content. The inward facing content is really, that's the gold. Included with that are file repositories. We have everything: documents, spreadsheets, photos, CAD, scripts that has been written, not all the way back 30 years, but going back to maybe like 2004. And during a given year, all current documents live there, accessible by anyone at any time. So nobody's sitting there going, what's our current estimate for the span right now? I'm in the lab, it's 10 o'clock, and I would like to do some work. they don't have to wonder what that data, where that data lives. We also have a wiki system. I like to call it the how-to, very short, descriptive write-ups, photos, processing, diagrams or documents, how to make something, how to wire up a speed controller or our particular speed controller, and then links to the repository as well. So pretty hard about, okay, you put that information there, but make sure the links are there as well so that people can actually find the information that was utilized. In terms of me as a faculty advisor, that last bit there about documentation, that's something that I have to say every year, remind them of the importance of it, how this should work, and make sure their practices stay up to snuff over there, because I think that goes quite a long way. I missed a bullet point there in terms of things that we document. Also, our purchase order log is on one Google sheet every last year. Has its own tab. So when we need to find a particular product or a vendor or something that we've used before, we don't have to go to Google first and see what comes up, but we can go right to the source of what we ordered in the past. Lastly there on this slide is alumni participation. I already mentioned weekly meetings, but also quite a bit of participation with design reviews. Our design reviews are, milestones that bring a design to a close. It forces the team to all come together to a stopping point for an entire aircraft. We hold two major design reviews. One of them is November, that's our preliminary design review, followed by CDR in February. So the difference is preliminary is very conceptual overview, trade studies, their planned approach. They may not have actually built an airplane just yet, but focusing on the subsystems. And the idea here is they're seeking advice in manufacturing or analytical insight. If anyone in the audience remembers something from previous years that they might want to bring up, then they can point them in the right direction. Moving to the critical design, this is where we have our final config for competition. It's where they attempt to draw the line in the sand, have some sort of demonstrated performance, flight test, and just validate their design. And ultimately, it's the last chance for us to make major changes. The event is held on campus and online. We would hold online regardless of a COVID year or not. And we typically get at least 30, industry sponsors, former team leads, alumni, faculty members, so not current team members that attend each of these events. Cohesive efforts certainly are required for putting together any of these design reviews. Like I said, the whole plane has to come to a stopping point. And something that really helps here is the directions and the goals are set in September. As soon as we do that score analysis, we identify 2 or 3 things that need to be the focus of every last thing that the team does. And it'll come up in meetings. If somebody presents analyses or is thinking about doing some other work, if it's not going to align with any of those 3 goals, the biggest fish to fry, if you will, then they just need to do something else, spend their time helping another group or working on another big part. So that keeps us out of the weeds of looking for the 0.5% solution. How much bigger should our winglets be or not? Or heck, if we just got rid of them, could we increase 10% in performance on some other subsystem if we focused on that instead? So it really helps keep the team focused and all driving towards common goals. All right, so as for the dollar amounts, the support structure is really no getting around the money, starting with the goal. So for me, the goal is build and maintain a team's foundation, and this is proven to require department level, school level, and university support. A faculty advisor, that's myself. So this is not typical service, as someone pointed out before we got started. There's nights and weekends, lab safety, a lot of hours involved. So hopefully your program can offer teaching credit, or does, as they do for me. It essentially gets me out of teaching a class each year. Industry advisor, actual dollars for their time. So you might get lucky with some volunteer effort, but expecting them to do that for 30 straight years, I don't think is a reality. But it's their time and their expertise that you're looking to inject into your team. And so for what we do with Wyatt is he is a part of our adjunct faculty. Alumni involvement, I say some money there, but it's just for like food at design reviews, taking care of your guests when they come to on-campus events. Lab space, team, in my opinion, really needs to have their own workspace. This is their think tank. This is where they can lay up a full airplane and not have to worry about sharing that. I know space is obviously hard to come by, but it's worth fighting for. And even though we have space, it's something I continually have to fight for to maintain or to keep. If you are at the luxury of having a lot of space, I highly recommend that you have separate manufacturing and say analysis management areas. Just like you would in industry, you would have, you know, the analysis work happening here, and then you go down to the lab and build. Maybe these two places are next door to each other, but it's much different than here's your one room for your laptop and for your fiberglass to get laid up on at the same time. How much does it cost us? Anywhere between 10 and 20K just for raw materials and electronics. We could be a lot leaner, I think. I think if you're starting from scratch, there's probably some startup capital to put you around this, you know, this range. But if you have access to machining equipment and lots of other things that are needed to build a plane, you could probably pull this off in a year successfully. Between $5,000 and $10,000 would be my guess. Travel depends on how many people you're sending. We typically send the major contributors. It doesn't have to be the engineering leads. For example, if they weren't a major contributor, they probably won't go. But we do make sure some of the highest contributing general members go each year. It's super important for just to gain the competition experience to understand what game day is going to be like. This helps with knowledge retention and just passing the torch to the next year's leadership. And I go to competition as well. And I point that out because I just don't see a lot of advisors at our competition. There's 90 some teams that go in a typical year. And I don't know how many advisors are there, but maybe it's 20, maybe. And definitely a huge shout out here to Ron Blackwelder, Blaine, and Mark Page, who's not shown, for figuring out a lot of this stuff out of like what a successful model could look like in terms of, you know, how are we going to fund this team and what are the things that matter? What are the things worth fighting for? And now it's my job to continue to fight for these things to make sure our team stays successful. Last little bit here is lessons learned from industry. So from my work in industry, I saw a lot of, you know, how you can boost productivity by just providing a little bit of technology that can improve efficiency. And ultimately, the idea of making an environment where people want to spend long hours. So this is where I just take a step back and say to myself, what would I want if I were going to live and work here? And I think it's important to do that because our students probably haven't worked anywhere else yet. They haven't seen some of the stuff that's in industry to even get these ideas that could make a difference. And there's the little things like a space mouse. You know, this is like the professional CAD mouse. I bought some of these for our lab, and the students' minds were blown because they'd never seen such a thing. They're doing these highly detailed CAD designs on a trackpad on, you know, on a PC. So once they had this, you know, they were super enthused to start living in the lab more. Multiple monitors, you know, if I'm in industry, I want 2 displays at least. These students have their laptops, so if they can dock to a better workstation, see more, and collaborate more, that certainly has boosted our productivity. Little things like a stereo system, make sure that place can be fun and jamming. And maybe it's the medium things. We put a large display in there, which has worked great for throwing up our CAD drawings without taking up either laptop space on a table or having to print out drawings that are going to take up limited table space. And that has also been quite nice to have for showcasing our lab whenever we give tours. And sometimes it's the larger things. So if you have the budget, a nice high-powered analysis workstation can boost productivity, give the students you know, a real workhorse to crunch on. And so in my opinion, I view these as like non-recurring expenses. Okay, maybe every 5 or so years I have to replace something. But it pays huge dividends and keeps our team rather enthused to kind of operate in what seems like a, you know, kind of a real engineering startup experience. And yeah, feed them too. If you have an extra $50, find some sandwiches. That always keeps them going into the late night. hours. All right, so as I summarize things here, what has been the result? Well, we're able to produce a student-run team that fosters growth, both in terms of technical, interpersonal, and professional development, obviously fostering teamwork as they work through these design challenges, and critical thinking as they attempt open-ended design projects. Hands-on problem solving, which is a huge aspect to, I think, the undergraduate experience, and this is where the manufacturing experience comes into play, where they typically gain a lot of that. And it also is fostering alumni and industry engagement throughout the year. All right, so what we're doing ultimately with these teams is kind of emulating that industry and that startup experience with the design teams. It gives them opportunities for demonstrated ownership of the things they're doing, the stuff that comes through by way of conversation, that they've had to make the tough decisions. They know the fine details about suppliers and whatever it might be on their subsystem. This is the stuff that's really going to make them shine during an interview, and I think also make them just better engineers as they make tougher and tougher decisions later on. It also gives them that opportunity to communicate, transfer knowledge, and operate in this idea of foundation first. So make sure what they're doing isn't going to be gone when they graduate, but it's going to benefit the team for future success. All of this ultimately creates opportunities, industry jobs, obviously, but what we're doing with these teams is essentially on-the-job training. I hear stories from recruiters all the time of what they're going to do. Instead of a career fair, they would just rather come visit the team in their lab. So they're actually bypassing our career fair or downsizing our normal career fairs just to spend time going to all these individual teams, because these are the students they really want to hire. And the stories I hear are interns making flight parts. And I'm not joking about that, but they are capable because they've had this experience and they're ready for prime time before they even graduate. It obviously creates opportunities for graduate studies as well. I particularly like to see some very interesting and unique senior project ideas, you know, dynamic thrust stands attached to cars, things that could help quantify dynamic propeller performance that we couldn't do in, say, a wind tunnel because of scale concerns. And this has also been huge for recruiting and future students. In fact, I have given 2 tours this summer from cold call. One's a sophomore, the other's a junior in high school, heard about our AeroDesign team, somehow checked out our website, reached out to me to see if they could get a tour of our space. Aside from that, I noticed all of our applications mention 1 or 2 of our design teams. That's really getting the students' interest and helping us recruit. All right, so with that, I just want to thank everyone again for listening to me chat here about design teams, my spin on what I think makes us successful, and just an overview of how we can operate here at USC. I'd be more than happy to take questions or reach out to me at any point if you have design team topics you'd like to discuss.